Hello, this is Dr. Leslie Ann Asmus, and in this recording session, we'll continue with our focus on discrete random variables and associated probability distribution. So far, we have talked through this is the third recording session. We first started with what are random variables in general. We talked about what is a discrete random variable, the probability distributions associated with these. We talked about the expected values in general and variance for random variables, discrete random variables, and then had a brief look at Chebyshev's theorem. We then took our focus and said, you know what, there certainly for discrete random variables, there are lots of possible probability distribution functions. And in the last recording session, we looked at just a few of the most common ones, namely the uniform distribution, the binomial distribution, which was, again, repeated Bernoulli trials. The question at hand for a binomial was, out of n Bernoulli trials, how many successes do you get? So we talked about ducks, but we also talked about, suppose you flip a coin 10 times, and you look at the random variable, how many heads do you get in 10 flips? And how could you describe, the probability of getting one head, the probability of getting two heads in exactly 10 flips? We then looked at the geometric distribution, which is, again, repeating Bernoulli trials, except the focus was different. And instead of saying, out of exactly this many predefined trials, how many successes, with a geometric, you say, well, how many of these trials do I keep having to do until I get my first success? And we note that for these Bernoulli trials and the binomial and the geometric distributions, that probability of success on one of those trials was staying constant. So with the duck example, I don't remember, 0.15%, 0.15 probability that a one duck would be infected with whatever that terrible disease was. But we noted that P, so we called that P, the probability of success on one trial. And that stayed constant in both the binomial and the geometric. What we're going to look at, turn our attention to, we're going to look at a few more of these very common probability distribution functions. The first of which is actually then an extension of the geometric. We go beyond and say, okay, instead of the first trial, we're looking for how many Bernoulli trials do we have to keep repeating until we get exactly our successes? Okay, notice that this is the negative binomial distribution. The reason it's, you think about it, binomial you specify ahead of time. I'm going to do 10 trials. I'm going to do 30 trials. How many successes in these number of predefined trials? With the negative binomial, what we're saying is, okay, I don't know. I might have to repeat the trial 10 times before I get my fifth success. That's not saying, so geometric, we said what's the probability of having to do 10 trials before the first success? What's the probability of doing 5 trials before the first success? With negative binomial, we say, okay, what's the probability that I have to do 10 trials, and on that 10th trial, I get perhaps my fifth success? Exactly our successes. Note that with a geometric, what we talked about before was, we said what's the probability that the random variable y was equal to 10. We had 9 failures, and then on that 10th trial, we had our first success. So that was y was equal to, what's the probability y equal to 10 in a geometric was 9 failures, first success on that exact 10th trial. Then we stop. In this case, we look and say, okay, what's the probability that y is equal to 10, and on that 10th trial, I have my fifth success, let's say. So what we're going to do with this negative binomial, I know I've been going on and on. Okay, let's go focus on it. Definition, a random variable y reflects the total number of independent identical Bernoulli trials. Outcome of each trial could either be a success or failure, a defect or a good one, however you want to look at that. But there's 2 possible outcomes on one of these Bernoulli trials. Repeat the identical independent Bernoulli trials until and including the R success. Then Y, the random variable Y, is said to have a negative binomial probability distribution function defined by, okay, so here's where we go with our mathematical notation. Probability that Y, our random variable, takes a specific value, little y, is equal to the probability that the first Y minus first trials contain R minus 1 successes. And then the Weiss trial is success. Okay, so let's put some numbers to this before we go looking at the formula. What's the probability that Y is equal to 10? Okay, well that means that on the first 9 trials, and let's say I'm interested in 5 successes, what's the probability that I had to do 10 trials to get exactly 5 successes? Well, what does that mean? That's the probability that in the first 9 trials, there were 4 successes, and on that 10th trial, boom, there came my 5th success. And then, of course, I stop, right? I don't have to go to an 11th trial or anything like that. I've got my 5 successes. So again, let me say that one more time. So, and I like to put numbers to these kind of things. What's the probability that Y is equal to 10? When my interest is to have exactly 5 successes, that probability that in a negative binomial distribution random variable, that I have the probability that I had 9 trials, and within those 9, I don't know whether it was a success, 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 4 successes in a row, and then 5 bad ones, or if I had 1 success and then I had a whole string of failures, and then I had 3 successes in a row. I'm not saying anything. All I care about is in those first 9 trials, there would be 4 successes. That's the R minus 1. So 5 would be R. R minus 1 is the 4 successes. And Y is equal to 10. So first 9, 10 minus 1, the first Y minus 1 trials, 9 trials contain R minus 1 successes, 4 successes. And then boom, on that 10th trial, I have my 5th success. So that's kind of putting some numbers to this. So what is that equal to? As you see here in the yellow, that's the probability of Y minus 1. First, Y minus 1 trials had R minus 1 successes, and then the Weiss trial is a success. So how do I figure out what the probability of R minus 1 successes in Y minus 1 trials? Well, that's R minus 1 chosen from Y minus 1. So go back and say, okay, that's staying to the 10 example. So that's not, if Y minus 1 is 9 and R minus 1 is 4, so 9 choose 4 are all the different ways that I could get 9. I got 9 trials, and in that mix I had 4 successes. So that's giving me all the different combinations of success, 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 and then 5 failures all in a row. Or maybe I have 1 success, and then I have, let me see, first success, and then, here I go again. First success, and then, let's say, 5 failures in a row, and then boom, I had 3 more successes. So all different ways you could get that, right? In 9 different trials, 4 successes. And then, well, so Y minus 1, choose R minus 1, and then P, probability of success on each one of those trials that were successful, and I wanted 4 of those, or R minus 1 in general form. And then 1 minus P, of course, is the probability of failure. So what did I have? I had 10, putting numbers to it, 10 minus R, 10 minus 5 would be 5, right? So if I'm looking for 10 trials, 5 of which are successes, then that would leave me 5 failures. So that's what the Y minus 1 is giving us, the exact number of failures we're interested in. It happened it was a 10 and a 5 and a 5, but think of all variations of that. Suppose 10 trials and I was only interested in 3 successes, right? And you can juggle that around. Okay, so in the yellow, basically, we're focused on those first Y minus 1 trials and having R minus 1 successes. Then we have in the exact Weiss trial,